Okay, let me do a little recap of what we did yesterday so that we can get it into the right focus today. First of all, I showed the following. This is the typical battery, or the schematics of a battery. Shows the electron flow, all those red balls that are going along the green cable. Let's call it a copper cable. So here you have the electron flow. You have electrons going from atom to atom. Okay? And they get out of the right-hand side there, which is the negative pole, and that's the lead pole, and it goes all the way to the other side where we have which is the positive side. That's where the electrons end. That's where they want to go. That's what's drawing them there, and that's the lead dioxide. How did we create this? Well, we created them chemically by having them react with the bath of sulfuric acid mixed with water. Okay? Actually, what you're staring at is not absolutely correct. It's a little misleading. What it should look like is more like this. We should have the electrons really spiraling around the wire. That's what Fleming's left-hand rule tells us, and that's also what's been verified in the lab. Electrons, or a charged particle, you can also say a charged ball, in a magnetic field will spiral around. It goes in circles, and since it goes forward, it ends up describing a spiral pattern. Okay, so what are we proposing? We're saying that that reaction, it's going to cause the molecules to spin. What I'm showing here is the lead on the right. It could be the lead sulfate, but I just put the lead atoms, and they're spinning. And if you have your eye at the bottom of that, you should see it spin clockwise. The one on the left, where the lead is, that should be going counterclockwise, and that's what I'm saying that the reaction, the chemical reaction, induces. The ones on the right move clockwise, and the ones on the left move counterclockwise. And the reason for that is molecular, because keep in mind that when two molecules connect and they form a compound of some kind, form another molecule, they can do so only in certain ways. When you have a chemical reaction, the whole molecule aligns itself in some way in order to make the reaction happen. It just can't do it in any old way. On the right side, we have the sulfuric reacting with a plate, and it aligns it in such a way that the spin that the lead had is simply aligned in such a way that it goes clockwise. And that same reaction on the left-hand side compels the lead, in this case, to go counterclockwise. So that's how we encounter the battery. That's how you buy it. This is a charged battery. What happens when we put a cable onto it? Well, then at that point, and we'll assume it's a copper cable, so that green with the orange balls, those we're going to say those are copper atoms. Well, what they do is they follow whatever they're in touch with. And since the lead atom on the right were twirling clockwise, that's what the cable does on the right side as well. The cable starts going clockwise. If you take that all the way around, you end up with counterclockwise. And that's all that Mother Nature understands. Mother Nature does not understand what a positive or a negative is, what a north or south pole is. Mother Nature only understands clockwise and counterclockwise. That's physics. The rest is just artificial math. So what we have here is a vision of what is likely to be happening inside a battery. You have a chemical reaction. That chemical reaction moves the lead in each side, in each plate, in one case clockwise, in the other case counterclockwise. As soon as you put a cable stuck to it, the cable imitates or gets that zap from the terminals, and the circuit is completed all the way around. What you have is starting clockwise, going to counterclockwise. No negative, no positive, no north, no south pole. That's the story as far as the battery is concerned. Now, this is the model that we have. You have two atoms, they're bound by a rope, and one of the threads comes out loose, and that's going to swing around. Those threads that are swinging around, those are going to form the magnetic field. These two atoms are aligned, and if they spin in the same direction, we have electricity. Here we have the two electron shells, and we have a whole bunch of other electron shells between them. And again, I just drew them as round balls. They're swinging all the threads around. What you're seeing is in the direction of your eyes, we have current, and 90 degrees to that, you have the magnetic field, which are the threads that are swinging around. So whenever we talk about current, electricity, electron flow, there is no flow. What we have is simply a bunch of atoms that are twirling in place. And that's what I'm suggesting for the lead in the case of the battery. What we're saying is that the lead atoms are twirling in the same direction. And that's what's causing electricity. So electricity, current flow, under the rope model is a bunch of atoms twirling in place. That's what it is. And if you put your finger at that end of one of those two ends, it's going to twirl your finger, and that's when you get the shock. So that's essentially what I'm describing there.